Suppose we wanted to do the same exact thing only with a DICOM image, a 16-bit image. Right? So now I've got this very interesting idea that we should be able to read in a DICOM image just the same way we got our image, but we need a different decoder, right? We need the DICOM decoder. And so somebody did a color decode. I think we did a color quantization, only 16-bit. And this, Rich, I think is your code. Yep, look, it's got your name on it. So when you ran it, and your question is, did I do a proper median cut algorithm? Let's see if we can't run your code. Let's see, the input is here, and the output looks like this, and here it is requantized. And what you did was you gave us a nice parameter at the head, which said let's reduce to a given number of colors, and you can pick however many you like. We'll pick 5. And there it is with 5 colors. Fair enough, right? So now what I'd like to do is I'd like to do an analysis of your code. Maybe we should look at it, huh? You don't mind that we're looking at your code, do you? Okay. So let's see what you did here. First thing you did was you said select a DICOM image, and then you called get a DICOM image. But what you did here when you said get a DICOM image is you got an AWT image. Now, in order to get an AWT image, you must have done a 16-bit to 8-bit conversion. So right now what we are dealing with here is a 8-bit image, right? Right there. Then you looked at the image and you said that's an original image. But in fact what you did was you already quantized it to an 8-bit value. Someone did the quantization. Now you're saying, well, let's get a requantization of PELs. Now where did these PELs come from? So get DICOM image had a side effect where it populated the PELs. And these are apparently short PELs. And then you took the short PELs and you called reduce number of colors. Then you took the short PELs and you did what now? You put them into the short processor. The short processor you called create buffer image, and then you displayed the image. So at some level we want to see the PELs that were created from get DICOM image. So where are the PELs? Here we get the DICOM decoder, we get the file info, we call for an image reader. Now the image reader went and got us an image. But you then went to the image reader and you said get short processor, and the short processor gave us the PELs. But what you returned here was an image, but you had as a side effect the creation of the PELs. That's the 16-bit PELs for your requantization algorithm. So what I'd like to focus on next is your solution for requantization. So requantization is using 2 parameters. One is the 16-bit values that you were able to get from the DICOM decoder, and the other is the total number of colors that you want to requantize those values to. And you start by finding out what is the maximum value. Now if you were using a lookup table, you would then proceed to initialize the lookup table so that the maximum value was used as the length of the lookup table. So then you wrote, if the number of colors you've specified is greater than the maximum number of colors, is that the maximum value or the maximum? It's the highest value. It's not the number of colors. So if the number of colors is greater than the highest value, then you have printed out some sort of an error and you exit. So then you say, okay, let's get the histogram based on the maximum number of colors in the input data. And then you created this thing called data out. This must be the requantized version of the image. So I'm just going to put in a note, create requantized image in data out. And now you've got a lookup table. How cool. So you've just built the lookup table so that it's the same size as the histogram. Now you've got this thing here called rep colors. What is rep colors? And why is that different from the lookup table?
So rep colors is used to make the table.
So then you did a thing here called segment window. Now, if we look at the algorithm statement, it says here, median cut no histogram with recursion versus median cut with histogram and no recursion. So I say that you're using the first variation of the algorithm, median cut with histogram, no recursion. You input an image and the number of colors, K. You compute the 16-bit histogram, which it looks like you did. You count the number of pixels, N. That's the total number of pixels. You compute the number of pixels per color. Now, what you've done here is you've gotten to the histogram length and divided it by the number of colors. But that's not quite the same thing, is it? So you've diverted from, what I would have said is, look up how many pixels you have. That would have been something like data out or data in dot length. So why did you pick histogram dot length?
My goal was to kind of figure out how many colors we wanted in the end, segment the histogram into that many segments, figure out the most popular color in each segment, and use each of those popular colors to represent the final image.
So what we're doing here is, instead of creating the same number of pixels per color, is you're dividing the histogram into K segments such that there are going to be so many bars per color. I'm not sure why you would do that. So maybe this is why you're wondering if this is a median cut algorithm, because I'm thinking it isn't. It's close. But what I would have done in here, according to my algorithm, according to my interpretation of the median cut algorithm, is that you want N over K equals PC, which is equal to the number of colors per pixel, and that should be constant. That is the number of pixels per color. I got it backwards. Number of pixels per color, and that should be constant. So if you knew that there were 1,000 pixels and you wanted 100 colors, then you would get 10 pixels assigned to each color.
Is it the number of colors in the input image or the number of colors that you want in the output image?
You want the number of colors in the output image to be a parameter. So that's K, the number of colors in the output image. Presumably that's that's smaller than the number of colors on the input image.
Jordan, do we need the number of colors on the input image?
The number of colors on the input image is not something you need, but it is something that you can compute based on the number of non-zero bars in the histogram.
I mean, I could be wrong, but I thought when I met with you in your office, you said that I needed the number of colors in the input image.
If you read the algorithm as it's printed in the document, it says input an image and the number of colors. That's the number of colors that you want to requantize to. So when you run, I don't wish to put too fine a point on it, but when you run the median cut algorithm using j2d.gui.main, something happened. You open, let's open a color image. We'll open the airplane. And now what we'll do is we'll run the median cut algorithm on the airplane. So this is color quantization, median cut. And now you can see that we start with different sorts of numbers that we can requantize to. Usually we start with 24 bits per pixel, which gives us 16 million different colors, but I can requantize to just 4 colors. So I want to know what I want to requantize to. So when you run the requantization algorithm, what you're doing is you're starting with a large number of colors, and then you create a smaller number of colors. And you have to know in advance what the smaller number of colors is, because that's a parameter. That's one of the button presses here.
Yeah, that's right. Okay.
Right?
Yeah. So it's the pixels in the input image or the colors that you want to be.
Yeah. So someone might tell me that there's I don't know, 256 by 256 image here. At a guess. I could probably find out, but it doesn't really matter. And then data on filters. Does it tell me? It gives me a lot of information. Yes, in fact, it is a 256 by 256 image. So I can tell you the total number of pixels. There's 65,536, which is the product of 256 by 256. So there are 65,536 pixels, and when I reduce it to median cut algorithm with 256 different colors, what that's saying is that there will be 256 pixels for each color. That's what median color algorithm, median cut would say. So what we want to do is we want to take the total number of pixels and divide by the number of colors. Yes, sir.
Sorry, how many colors are in the original?
We don't know that. We could try and find out. But this is saying with median cut, make it so that there are the same number of pixels for each color. So if there's 65,536 pixels, and you want to divide that into 256 different equal segments, then it turns out there will be exactly 256 pixels for each color if you take the total number of pixels and divide by 256. To answer the other question about color info, I don't know if I have an info algorithm that tells you how many total colors there are. I got an RGB average, a standard deviation. It does not tell you in this printout how many colors there are, but we could compute it. No, but you don't need to know it. Yeah, there's a thing called the color hash, which will actually create a hash table which will store all the different colors, and then will count all the colors for you efficiently. If you want to do that in 24 bits. If you want to do it in 16 bits or 8 bits, it's a lot easier with a histogram, counting the total number of colors. Making a 24-bit histogram is possible if you have the memory. So then you want to sort the pixels by value and divide and conquer the pixels at P sub C pixels at a time, binning by min and max range. So then I gave you some, oh no, that's the wrong algorithm. Sorry. Compute the number of pixels per color, that's step 4. Divide the histogram into K segments such that there are P sub C pixels per segment. So how do you do that when you're dealing with a grayscale image? Right? You march along the histogram and you count the number of pixels in each one of the bars. And as soon as you exceed P sub C pixels, then you stop and you say that's a segment. And you keep going with the histogram until you get to...
when you say that's a segment, is that what you say that's in the lookup table? Or?
Yeah, then you have to set your lookup table. So the lookup table might be valued 0 for the first value, and you look at the number of pixels at value 0, and if it's not equal to P sub C, you go to the next value in the lookup table, and if you still haven't exceeded the number of values in P sub C, then lookup table index number 1 will also equal 0. And then you go to the next value in the next bar of the histogram, and you compute the total number of pixels by adding up the prior values in the histogram and saying, aha, we've reached P sub C. So now you've got lookup table value 0, 1, and 2 all equal to 0, and then you start again, and as you set those next lookup table values, they'll all be equal to, let's say, 1. And that'll let you march along. So then you map the segments into a lookup table that enables the fast mapping between pixel values and the requantized values, and then you use the lookup table to requantize the image and display. So the tricky bit is the 16-bit lookup table.
I'm like waiting for this.
So then your next question is, how do I use a 16-bit lookup table in order to modify my image? And I think, Rich, you have done that. Because, well, here's your histogram. Here's the representative colors. Now, do you set the lookup table? Yes. So why is it that you needed two different arrays, rep colors and lookup table?
So what I wanted to do is like figure out what I thought were the best colors to prime my image, the best colors to represent on my image. So that was going to represent the color for post baby, and then I made a lookup table that was the same length as the histogram, so I could go through each of the colors that existed,
Mm-hmm.
go through the image and using my lookup table to reassign each pixel based on that.
Yeah, it looks like you did two passes here. In the first pass, you set the lookup table. In the second pass, you set it again.
That was to handle the remainder of the histogram. Because like if the segments didn't quite hit the end of the histogram, I just took the remainder and treated them as the last segments, the same way the last segments are.
Tell me again what a segment window is.
So that was the length of your histogram divided by the number of pixels that are encoded.
Ah, I see. Okay. Now, what would happen if I changed this and made it n over k? Would that break your code, do you think? Probably, right? I'm just wondering why we wouldn't use n over k here. Is that data in dot length? Yeah, your segment code is looking a little confusing to me. We got to start with a median, with a a DICOM image. Yeah, he didn't like that. Array index out of bounds exception, 356. It looks like there's a value in there that goes beyond the end of the lookup table.
Yeah, so the lookup table is only the length of the histogram.
Well, that's what I thought that was weird.
So
The lookup table should be equal to the maximum value of the input pixel that you encounter.
So I figured that the highest color value that I'd ever see would be the highest value of the histogram.
No, you went to the histogram length, not the highest value of the histogram.
Sorry, the highest color represented in that histogram.
Oh, that's interesting. And why should that be?
You won't see any color.
Ah, okay. So get histogram should be max. What's max?
It's the highest color value in the image. So the histogram isn't 2 to the 16. It's only as long as the highest color value that was in the image.
Yeah, so how come we got values in there that went out of bounds, like 356?
Because you changed your data.length. You changed it from histogram.length to data.length.
Oh, okay.
So you ran past data.
Data.length doesn't make sense, does it? Is it okay now?
Yeah.
All right. All right. That's interesting. Wow. So if I wanted to do a lookup table for 16-bit images, would I be able to do that? Would you be able to do it? You saw the details now for 8-bit images and also color images. Now you want to try and do it on your own with the DICOM image, right? You've seen it happen a couple times now. Here we have the 8-bit values being mapped to, the 16-bit values being mapped to 8-bit values. That's legit. You got a question?
Yeah, were we going to go over the homework that was due today?
We sure can.
Okay.
I just wanted to put this midterm to bed because some people had questions. And you're still confused.
No, I'm like, I have the max colors. I'm looping through the length of the histogram, and I say if the index of the histogram is greater than the number of pixels that I want that per color that I calculated, then I don't know what to set the lookup table to. And I said if it's not, if the index of the histogram is less than that pixels per color value, then I sum up consecutive bars. But I think what I'm setting the lookup table to is wrong, I think. But I feel like everything else is on the right track.
So what you want to do is you want to march through the histogram until you exceed or equal to the number of pixels that you intend to have per segment.
Okay, yeah.
So you got that?
Yeah.
So let's assume you have a histogram, and I'll just number it with values. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 different possible values. Let's say there's 23 pixels here, 34 pixels there, 23 there, 22 there, 56 there, 78 there, 56 here. I'm making up numbers, 34 and 23. And now I'd like to find out how many pixels are there in the image, and so I'll set that equal to the sum of the prior 8 values. And so now I see, aha, there are 349 pixels in the image. Now somebody says to me, but I only want, make up a number, 3 colors. So I have, according to this, created a value called n. So I write n equals, right, where n is equal to the total number of pixels in the image. And I can get that from the histogram. And it also tells me I need k, where k is equal to, and we said it was going to be, let's say, 3 colors. And then someone said n over k equals p sub c. So now what I can do is I can say p sub c equals, and then I set that equal to n divided by 3. So that says there's going to be 116 pixels per color. Right? So now what I can do is I can create a sum. And that says 23. That's equal to sum of the prior two, and that's 57. That's equal to the sum of these 3, and I got 80. That's equal to the sum of these guys, and I got 102. That's equal to the sum of these guys, and now what do I have? 158. So what that says to me is the lookup table will be valued 0, 0, 0, 0, 0. Now I have to start again. That equals the sum of this. That equals the sum of the next two. And now it says 134. Aha! So I've achieved 116, so this becomes 1, 1. And that's just a classification for the pixel. And I can map those into any arbitrary color I like. Maybe 0 would be mapped to 0. 1 could be somewhere in the middle of 255 to 0, so maybe it's 128. And then the next two will be mapped to sum of this. We're starting again, and that'll be sum of these two, and then we're done. And so then these must be 2 and 2. So the median cut algorithm says that the number of pixels per color will be approximately the same. And so they are. 116 or so pixels are being allocated to each one of the classes. So now you can say, aha, how shall I remap these classifications? Well, 0 is legit. This might be 128. And this might be 255 and 255. And there you go. Median cut algorithm. So now you use these values in here. Well, let's see. You need to have these values into a lookup table whose contents is this. And as the values are looked up, those contents will be returned. And the median cut algorithm will be implemented then on that image with the speed of a lookup. What do you think of that?
What you're saying makes sense. I can talk to you after that. That's okay.
Sure, but I'm here for questions. Does anyone want to talk about this midterm anymore? Shall we look at the where's the grade center? I'm having trouble finding it. Full grade center needs grading. So we've got, what was this assignment? just want to bring up the assignment. Ah, okay. So here's the image sequence synthesis. You guys were going to do a panning over the image, and you can control the speed of your pan, but you don't necessarily control the speed of your playback. The speed of your pan will be defined by how many different pixels you adjust a window into your image as you move from one frame to the other. But the speed of your playback will just be the rate at which the images are presented, right? So what you're really doing is image sequence synthesis from a given input image. You're doing an electronic pan across the image. With that kind of an image sequence, you should be able to output a GIF animation, and the GIF animation should be something that you can display on an arbitrary browser that renders images. Not every browser renders images. Lynx, for example, is a text-only browser. I use it all the time because it's text-only. It's very, very fast, and it has no flash. It has no plugins, and it's very good for retrieving data off of the web. So when you go to something like an image of a file or a disk drive or a file system, you just want to download it real quick. Lynx is really very good under Unix for that. It's also very good for Raspberry Pi if you don't feel like starting X. And when you start X on a Raspberry Pi, it takes a long time because Raspberry Pi is like anemic. Right? It's only an 800 megahertz processor. It's not meant for that. I mean, you can run X, just be prepared to wait. So how'd you guys do with this? Did all right? I can look at your code?
You want to tear it apart, yeah.
Sure, let's look at Kyle's code. Alright, so needs grading. How do we get back to needs grading? That's this. Can you render these files in Blackboard? No.
Yeah. Well, I just download. I gave you like GIFs that were already made too. You only really need the first one, or that's just the image.
I uploaded the images I used in the GIFs, and the Ferrari and Shiga grayscale are the images I used. And the code is just the code.
Oh look, it's moving. It's the world's slowest cheetah. Is that it?
Yeah, you said.
It's very ferocious.
I mean, that's what.
No. Yeah, it's good. Oh, it almost got big. Yeah, I don't know. I did a refresh, it got big. It's moving.
For what? Oh, it's video.
It's got very beady eyes. It looks like it missed dinner. And I know just how it feels. So, let's look at your code. Is that alright? You can do that, right? Okay. Download. Did that work? This is why I use links. Here it is. Show in folder. Okay. Copy. And then what we'll do is J for P, SRC, and go to the bottom. Maybe I can. How does one paste? If I paste now, will it just paste into something? No. Okay. Good deal. So, what's the story here, Kyle? So I can just run this, right? Will it prompt me? Does it matter how big the image is?
It needs to be grayscale.
Oh, it has to be grayscale.
That's what you said.
Oh.
Send video. Or else he said he wouldn't be able to quantize it if it wasn't grayscale.
Well, in fact,
I don't know.
it has to have 256 colors.
Yeah, that's what I meant. It needs to be 8-bit. It doesn't need to be grayscale.
It does not need to be
Yeah,
grayscale.
that's true. Sorry, my bad.
And if you use a median cut algorithm on a non 8-bit, if you have a color image with more than 256 colors, you can re-quantize it to 256 colors using median cut algorithm, and then you can make a color GIF animation out of it. Because GIFs are color.
No, it does work with color. It just needs to be 8-bit color. My bad.
Yeah, 8-bit color, not grayscale. Okay, so let's call this something. foo.gif. Whoops.
It's going to save 50 images where you put it.
Oh, really?
Yeah.
Holy mackerel. Why is it doing that?
Because you said you want 50 frames.
Yeah, but I mean, can't you just add the frames to the animated GIF encoder?
Because didn't we read it from the directory? That's what I did. I just did that way. I don't know if you want.
Yeah, I don't want 50 images on where this is at. Wow.
And they're going to be called image 0 or whatever, so if you have that, it's going to erase it.
Okay. Wow, look at what you did. Now what do I... Now what?
Select where you want to save it. And combine them. Actually, just do it on the desktop so I can delete.
I got confused.
Put in food.
Yeah, put it in food. See, mine at the top says, like, directions, so I don't know why they're not here.
Now what?
Now go to the win. Right?
Okay. Well, it certainly worked. Now, let me ask you a question. Did you have to create 50 different images in order to create your GIF animation? Couldn't you use the GIF animation encoder and just add the image as you created it?
I don't know.
Oh.
I was just doing it the way that we started in class, where you read the files in the directory.
Okay. Let's have a look at your code. So here is your code, and here's where you're producing these images and where you're saving them as a GIF. Then when you generate the animation, you read them in from a file, and then what? Then you add the images. So instead of saving them to a file, you could have added them.
Yeah, probably.
Could have just called add frame each time.
Yeah.
And that would have worked reasonably well, I think.
I guess I just did it the annoying way.
The annoying way.
Yeah.
Well, it certainly achieved your goal. But it worked. Yes, sir.
Can you tell me how he did the windowing? If he doesn't mind.
Yeah, I don't mind.
That's it.
So
I used something and then I put X for the windowing.
you did?
Yeah.
What did you do for the windowing?
It's
I see the start dimension, and then you went
yeah, get pixels.
X went one
Like grab the
pixel over for each frame. And then what's this increment here?
That's a moving one. It goes until the start dimension plus a number, I think.
Okay.
It's gonna do 50 times.
So it runs 50 frames, but the increment can be arbitrary.
If you change it, it'll move faster.
And if okay, so here's the speed.
It won't be as slow. Yeah.
Yeah.
And
So
it'll also be a shorter. It'll be a shorter thing too. It'll still be 50 frames, but it'll go. It'll move over the entire image a lot more faster.
right, it'll go faster. You'll have faster image flow. Now, how did you window the image?
The get pixels. It was right. It was right there. Um,
Up.
what I did is I divided the width. I knew I wanted 50 frames was a quick parameter that you can run it for 5 frames per second for 10 seconds.
Uh huh.
So I divided. If you go up, if you scroll up, you'll see where I set like the start, the dimension of the window. Oh no, actually,
I have a question.
Yes, sir.
The divided by 3, what was the purpose of that?
I just said I would arbitrarily have what I was displaying be 1/3 of the width. It was whatever size I wanted it to show. Because I wanted it to scroll. If I did the whole width, it wouldn't move anything.
So here's something called get subimage. And what that does is it'll make an arbitrary rectangle, and input an image, and then you can change X and march it along and keep width and height the same, keep the Y the same, and it'll just move right along, getting the subimages.
That's why I just did it by the pixels, because I didn't know if that existed.
Oh.
You use get crop image or crop. I use the crop one.
You could certainly do that as well. In fact, you can find all of these things if you are interested in seeing what I've implemented. If you go to j2d.gui.main and just play, right? Have fun with play. Experiment. Experiment with the image processing program. You'll see all of the different functions that I've got. So if you wanted to open up an image, let's open up this one, and then you wanted to go to shape, size, border panel, or crop panel. Crop panel is a good one too. So you use the crop, is that right?
Yes. It asks for image, object, and a rectangle on it.
Yeah. So here, if you change the, if you keep the height the same, but you move the width, that's not good, huh? How did you do it? I forgot how to use this. I'm throwing exceptions too. There it is. Yeah, you can animate the image in this way too, by changing the origin of the Y coordinate, and that's like a crop. That'll let you slide along and do an animation. So that'll work. That's a way to do it. I like the subimage part because it lets you grab tiles. When you're grabbing tiles in an image, you can make it so that the tiles are either overlapping or non-overlapping. And what you're doing when you're incrementing by 1 is you're getting an overlapping tile. But if you wanted to, you could break the image up into chunks and then do something with the chunks. Like, for example, when you do adaptive histogram equalization, you histogram equalize on individual chunks in the image instead of on the whole image.
So what's different about that method and the get pixels that I used?
It's accelerated by Java Advanced Imaging, which means that there are Java native interfaces to low-lying C implemented subroutines that make use of the SSE or MMX instructions.
Sorry,
It uses, right? Remember in computer architecture we talked about vector processing, single instruction, multiple data, and so you're doing the same thing on multiple pixels. Right? This is SIMD. So if you have a vector coprocessor, or if you have vector accelerated parts in your CPU, you can take advantage of them, but not necessarily in Java. So you can call the subroutine libraries that take advantage of these things in order to accelerate your code. So when you look at the border subroutines that I used here, the cropping, you see that they've been accelerated by Java Advanced Imaging subroutine libraries. So when you go to image utils, what did you use there? Right.
Like get crop or crop.
Get crop, was it? That sounds about right. Get cropped image. Get cropped image. So get cropped image, look at the implementation. It creates a parameter block which then gets passed into Java Advanced Imaging. Java Advanced Imaging is a whole subroutine library that's been accelerated on Java's virtual machine in order to link through Java native image implementations. This particular thing may actually not be that much faster than doing it in Java, but there's a whole bunch of other stuff, including transform libraries, that would enable you to get very high performance.
I use crop image too.
Use crop image, not get crop image?
Yeah.
Crop image here.
Yeah, that one.
So this crop image calls crop image with a buffered image. And that uses the Java native interfaces. So what that does is it treats the input image as a Java AWT image instead of a buffered image, but then it converts it to a buffered image, then uses the Java Advanced Imaging, and then converts it back to an image again. They're stored in memory. They're buffered. They're stored in a buffer. So yeah, when you look at something like a toolkit like image utils, what you're seeing is a lot of complexity that's kind of been hidden away from you. When I do something like show you how parameter blocks work, I'm kind of going underneath the hood of a high-performance car and showing you how the engine is tuned. But you don't need that in order to drive the car. So the question of how deep into the details you want to get is going to be a function of whether or not you want to get to be a serious Java image processing developer. But it becomes very Java specific once you start doing something like this. Very API specific. And I feel like that's too much API, especially if all you want to do is crop an image. Right? You could crop the image without any of this stuff, but it just wouldn't be as high performance. So there's a whole bunch of Java Advanced Imaging stuff. They didn't have that when I wrote my first image processing book in Java. Java Advanced Imaging came out after that book was published. So the entire book was done without Java Advanced Imaging. Somebody else want to have their code looked at, or are we out of time? We're out of time. Did anybody have any trouble doing the animated GIF? No? How about that pseudo-color algorithm? Wasn't that cool? How about if we use pseudo-color on our next animated GIF? Then we can make an animated pseudo-colored GIF. Now, my question is, what kind of problem would you envision happening if you started to do that? You could certainly input a black and white or even a color image.
I was thinking we can do pseudo-color in the image and then GIF. And then
Well, before you add to an animated GIF, you must do a color reduction. You have to do requantization. So what that means to you, the programmer, is you do not add images that have more than 256 colors to an animated GIF. Got that?
Yeah, my question was, you can use pseudo-color on the image before you start windowing it? Or do you window it and then apply the pseudo-color? I think you have two different results, right?
You could pseudo-color the image first.
Yeah.
Then you could create the animated GIF.
Yeah.
But if you pseudo-color the image, you're going to have more than 256 colors. So what you'll need to do after you pseudocolor the image is requantize the image, and then you'll have to create the animated GIF. So what we'll do is we'll write it up as a real quick sort of assignment here. It'll be a nice fun assignment. So building on your prior expertise, if you like, for making animated GIFs, and driving home the lesson about homogeneous point processing, we'll create a new assignment. Oh, what number homework is this?
6.
Is that right?
Yes.
Homework 6. Let's call it color animation. That sounds like fun, actually. You know what I'd really like to do is have you guys do an edge detection where we do a raster to vector conversion and then take the vector images and output onto the laser cutter. Huh? Huh? And then we can take your images that have been edge detected, and they could be like home pictures, whatever you like, off, and we just cut them into. I got a whole bunch of CD covers, and we could just cut them in. I think that'd be fun. Yeah, that sounds. Well, I don't know if it's the final, but it's fun. So let's see. Here's the deal. Input and image. Okay, that's good. Pseudocolor. Color the image. Okay. Requantize the number of colors to 256 colors using whatever algorithm you like. Probably median cut, right? Because we got some nice ones already. Median cut suggested. Hint. Median cut. Then output the image sequence as a GIF animation. Okay. Do not generate in image files, individual image files. Whoops, there goes that trackpad. Image files. Just one image. And how many files shall we create? We want create 50 frames. That's what we did last time, right? And play them back at, was it 10 frames per second? 5 frames per second? 5 FPS. Everybody got that? So now we have you can use any arbitrary input image you like. And it's due next week. And it's 100 points. And due next week at 5 p.m. What else? Anything else? Everybody understand the assignment? Ready to go home now?
There's just a method for pseudocolor, right?
Oh yeah. Well, I kind of did it in the lecture, but if you're interested in seeing, I forgot what I was doing. Oh, here. It might even be in image utils. Probably under get pseudocolor image, right? Get. That makes sense. There might not be a get pseudocolor image, but we did have a demo where you were pseudocoloring an image using a lookup table. I beg your pardon? Didn't I just do this with the lookup table? Here it is, pseudo color filter.
So would we need to apply a lookup table here?
You don't have to use the lookup table to do a pseudo color filter. I think if you went to pseudo color filter, there was a way to get a, well, maybe. You know what? I like the lookup table, and this certainly does it. This builds a lookup table and then implements it with the packing and unpacking of the pixels. Do you have to do it that way, is the question. Do you need a lookup table in order to pseudo-color an image? Wasn't there an example where we got a here, colorize. It's under image utils. So it's already there. All you have to do is colorize the image. So pass the image in along with whatever parameters you decide to use for the colorization. It has to be a number that ranges from 0 to 1, and a new image will pop out. So just colorize the image. How's that? Got that? Everybody okay with this? Brian? Yes? Alrighty then. Stop.